So the first language we're going to be talking about is 0 union 1 star, which is effectively all binary strings. We have this language called L1, and what we want to make is a context-free grammar for this language. Well, this has every single string in it, so we need to be allowing every possible string in the grammar that we make. Well, every single context-free grammar must have a start variable, well, a set of variables too, a set of terminals, and a set of rules. So we need a start variable. I'm going to call it S here, so this is the start variable. And we need a rule to actually generate the strings. Well, one string here that is obviously in this set is the empty string. So I need to allow ourselves to make the empty string. But we also have that no matter what string that we have made so far, we can always add a 0 onto the end of it. That's also a valid string. And any string that we've made so far, these might not be the same, we may allow ourselves to add a 1 at the end. And no matter what string that we have, it's either empty, or it ends in a 0, or it ends in a 1. And so therefore, no matter what string we've made so far, which is corresponding to this S right here, we need to allow ourselves to make a 0 afterward, but also allow ourselves to make a 1 afterward. And so therefore, this is a context-free grammar for this particular language. Now, there are many other types of context-free grammars we could have made. We could have had some other variables right here. We didn't have to put the 0 on the end. We could have put it on the front, because the same logic will apply. If we have made some strings so far, we can always stick a 0 or a 1 on the front, and every string is either the empty string, or it starts with a 0, or it starts with a 1. So there are many different context-free grammars that we can make, but this is one of them for L1. Okay, let's make a context-free grammar for this language, L2, which is the set of strings of the form 0 to the n, 1 to the m, where n and m are at least 0. So one thing that you should be aware of when making a context-free grammar for a language that's given to you is, what are the relationships between the counts here? So the count n here is relating the number of zeros, well, it is the number of zeros, and m is the number of ones here. And note that there's no correspondence between the n and m parameters. They don't have to be the same or different or anything. They're just independent numbers. And so therefore, we can treat them completely separately. So every string in this language always has some number of zeros at the start and then some number of ones at the end. And so therefore, we can actually write a regular expression for this. We can just say that it's 0 star, 1 star. Because it's just some number of zeros, any number that we want, because there's no restriction there other than being at least 0, and then followed by some number of 1. So we can make a regex for this. But what we're after is a context-free grammar. So every context-free grammar needs a start variable, so let's make a start variable right here. And then what we want is that we need to generate some number of zeros, and then once we're done generating the zeros, whatever that means, we need to be able to generate some more ones. But here, so one thing that we can do is, let's just make a bunch of zeros right here by having a 0 followed by s, which says you can add zeros on the front as needed, and then at some point later we need to switch over to ones. But it'd be an incorrect idea to do this, because if we have this right here where s is the start variable again, what could happen is that we can interchange these two rules. So therefore we could apply this rule, then this one, and then just go back and forth as any way that we want. And this is a bad idea. So what we want to do is to go to some other place where we can't access this rule anymore, and then generate the ones there. And so what I'm going to do is I'm going to go to a variable called p. So p is a completely new variable, where I can now make the ones here. So just like with the s variable, where it can make zeros, I can make ones here. And there's no relationship other than the ones being after the zeros. And now, once I'm done generating the ones, well, there's nothing after the set of ones here, and I can do this as many times as I like. So I need to be able to stop by making the variable go away. And so if we look at a particular example, so let's consider the string, say 2 zeros and a single one, then a derivation will be s goes to 0s, so I replace this s with 0s, which is this rule. Then I'm going to replace this s with another application of the same rule, so I get 0, 0s. Then now I'm done generating the zeros, I need to switch over to the ones, so I'm going to now replace this s with p, so applying this rule this time. So 0, 0p, looks like object-oriented programming. Then now I need to generate a 1, which is applying this rule, p goes to 1p. So 0, 0, 1p. And then now I need this rule here because this rule right here at the bottom, because every rule in the grammar otherwise always has a variable attached to it. And we need to make strings with no terminals at all. That's what the language of a context-free grammar. And we need to make a string with no variables at all, only terminals, because that's what the language of a context-free grammar is. And so now I'm going to apply this rule right here by making p go away, in other words, changing it to be the empty string, which is exactly what this is. And so therefore, this is a context-free grammar for this language, which is the regex corresponding to 0 star, 1 star. Okay, let's make a context-free grammar for this language, which is the... Okay, let's make a context-free grammar for this language, which I'm informally writing as the set of palindromes over the alphabet 0 and 1. So as an example, a palindrome. So recall that a palindrome is a string that's the same when... Recall that a palindrome is a string that is exactly the same when read in one way versus reading it incomplete. So recall that a palindrome is a string that is exactly the same forwards as backwards. So as an example, if we have 0, 0, that's a palindrome because it's the same one way as the other way. If we have the string 0, 1, that's not a palindrome because in this direction it's 0, 1 and this direction it's 1, 0. But if I add a 0 on the end here, now it's exactly the same forwards and backwards. And so note that we could have a string that is of length 2 or even any even number as well as any odd number. And so what we want to do is we want to make a context-free grammar for this. So again, every context-free grammar Of course, every context-free grammar has a start variable. So let's make a start variable here. And let's think about what a palindrome is. So if we have a palindrome right here, then what that means is that it's exactly the same forwards and backwards. Well, if we think about that, if we go this direction and then this direction, we must encounter the same character at the very beginning. In other words, the character at the beginning of the whole string is the same as the character at the end of the string because it's exactly the same forwards and backwards. So if I see a 0, for example, at the beginning, then I must see a 0 at the end. And if I see a 1 at the beginning, then I must see a 1 at the end also. And so therefore, if I see a 0 here, then what must appear in the middle? It must also be a palindrome because if we take the ends off, it's the exact... Because if we take the ends off, it's exactly the same when read forwards as backwards. And so therefore what goes in here is corresponding to generating any palindrome at all because there's no correspondence between what happens in the middle and what happens at the end. And so therefore, if S is going to be representing the set of palindromes, therefore I must put an S here. So 0 followed by some palindrome and then a 0. But also we can have a 1 followed by some palindrome and a 1 for similar reasons. Well then, what's the base cases? These are the inductive cases. Well, what are the really smallest palindromes we can have? Well, we can have the empty string. The empty string is exactly the same forwards and backwards. But if we look at what we have here, we'll never be able to generate this string because this has 0 characters, and these two rules add an even number, in this case 2 characters. So I'll never get any odd length string. But if we think about a string of length 1, it's exactly the same forwards and backwards. So therefore I need to add the base cases of 0 and 1 here. So now let's think, can we actually generate this string? Because we can obviously generate this string and you should do it for yourself. If we can we do this one? So that we can apply this rule, then this S can now make the 1 over there. And so therefore we have made a context-free grammar for all palindromes over 0, 1. Okay, so let's make a context-free grammar for... Okay, so what we're going to be doing today... So let's make a context-free grammar, actually 3 in this case, corresponding to 2 different languages, L1 and L2, where these 2 languages are context-free languages. So I have 2 context-free languages, and I want to form the union between them, as well as the concatenation between them, and then the star of either one. I'll pick L1 here. So if they're context-free languages, then we have 2 grammars for them. So G1 and G2 are context-free grammars for them. And what we want to do is we want to make a context-free grammar for these 3 languages. And it's actually fairly easy to do. So let's talk about the union one first, because it actually will generalize. So if we have the union of 2 context-free languages, then that means that either G1 can make the string that we're after, or G2 can make the string that we're after. Well then, what we can do is we can make a new start variable. So this is a new start variable. I'm going to call it S here, and I'm going to use S in all 3 cases. So then I'm going to add a rule here that says I'm going to go to the start variable of these 2 grammars. So let's call them S1 and S2 of these 2 grammars. Then I can either have S1 make the string that I'm after, or S2 can make the string that I'm after. There's one small technical problem though, is we gotta be sure that the context-free grammars we're dealing with don't have overlapping variables. Because if G1 has a variable called A, and G2 also has a variable called A, then any rule that G1 involves with A could, in principle, if we just combine the 2 grammars together, could switch over. And that can cause havoc. Whereas if we rename all of the variables in the grammars, then we have no problem whatsoever. Okay, so then what can we do now? Well, okay, so now let's do L4B, and we can do something very similar. What we can do is, again, a new start variable. It's still going to be S here. Whereas now I'm going to have not S1 or S2, I'm going to put S1, S2 together. Because concatenation of 2 languages says, pick a string out of here, and then combine the 2 together. Whereas here, what we're doing is making some string with S1, and we can't quit early because S2 is a variable, and we need to make a string of terminals. So S2 is going to make some string, potentially, and then that corresponds to generating a string in the original language. So then now let's make one for... So now let's make one for C, and that's L1 star. Well, we got to think, well, what is the base case and what's the inductive case? Because star involves infinitely many different languages in some sense. Well, one thing that you should be aware of is that in the star of any language is the empty string. So if we have an S here, it doesn't matter whether L1 can make the empty string itself, L1 star always has the empty string in it. So then this grammar must definitely generate the empty string, even if L1 did or didn't, it doesn't matter. So here I'm going to force that it can make the empty string, even if it didn't before. But if we don't do that, well, the star of a language is defined to be any number of concatenations that you wish. And so we can use this idea where we can go down into the grammar for L1, make a string, and then decide maybe we want to go again if we want to. And so all we need to do is to go into the start variable of S1, followed by going recursively to the start variable here to allow us to go in again as many times as we need to. And whenever we're done, we can just make that one S go away. Because whenever we're making this right here, we're only having one S being generated, which is later going to be replaced. So we're going to have at most one S occurring anywhere, which is exactly what we want. So therefore, we have made a context-free grammar for the union, concatenation, and star of two context-free languages. What's the fifth one? Okay, so let's make a context-free grammar for this language, which is the set of all strings of the form some number of A's, some number of B's, some number of C's, where the number of A's, which is what I is not equal to the number of B's, which is J. And what we want to do is to make a context-free grammar for this. Notice that the number of C's here, which is K, has no relation to the number of A's or B's, which are I and J here. So what we can do is we can forget about the C's and we just focus on the A and B part and then we can just focus on the A and B part and then deal with the C's later. So again, every start variable has every context-free grammar has a start variable. So let's make a start variable here, and I'm going to label it like this. So then let's think about how we're going to structure this. How do we actually tell whether or not the counts of two variables are the same or not? That seems a little weird. Well, all that we need to do is to think about this in a slightly different way. Another way of rephrasing this same condition is to say I is less than J or I is bigger than J. It must be one of those two because they can't be the same. So how are we going to relate these two together? Well, we're going to have a variable that corresponds to the I less than J case and another variable that corresponds to the I bigger than J case. So I'm going to have two variables called A, I less than J. You don't have to have the subscript here, it's just to help you. A, I less than J or A, I bigger than J. So let's deal with the I less than J case. So I less than J. Well, that means that the number of A's is less than the number of B's. But the number of B's could be only one more than the number of A's, or way more than that. It could be anything in principle. So what I'm going to do is I'm going to allow ourselves to make A's and B's an equal number, and then later allow ourselves to make as many more B's as we need to. So I'm going to say, I'm going to have a rule like this. So I'm going to generate one A here, recursively go into this same variable with a B. So that means that I'm going to, at this point, be generating them in equal number. So one A for every B, but of course we got to make at least one more B. So then I'm going to have a variable right here, which is called making B's, or I'm just going to call it B here. and its sole purpose is to make more b's. That's it. So I'm going to have more b's right here. So this variable b is just going to spout off as many b's as it wants, at least 0. And it's important that it's at least 0, although you could work it where b makes exactly, you can work it to where b makes at least 1 more, but I'm going to do it this way. Well, how are we going to relate the I less than j guy to the b guy? What I'm going to do is, notice that we have the same number right here, and this guy only guarantees to get at least 0 more b's. Whereas I less than j must generate at least 1 more b. And so therefore, to get down to here, I'm going to have this be my rule. So to get down here, so in order to make a string at all, I must generate at least 1 b right here, which does not correspond to an a. And so therefore, whenever this makes a string, I must have at least 1 more b than a, which is exactly what we want. Well then now, the only thing that we have to deal with is dealing with the c's at the end, but again, they don't have any relation to the I and j numbers. So one easy way of doing this is to have a variable right here that goes after both of these, because the condition of c is exactly the same as to whether or not the number of a's and b's is the same. Because the condition of where the c's are does not depend on the a's and b's at all. So I'm going to have a variable c here which just spouts off c's and nothing else. And it's exactly the same idea as the b here, but it's used for a different purpose. Okay, so that handles the I less than j case. So we have equal number, and I guarantee to get at least 1 more because of this rule right here. And if we need more, I can just apply this rule as many times as I want. So now let's deal with the I bigger than j one, and it's going to be a very similar idea. So I bigger than j is going to be I bigger than j, b. But then now, if we have more a's than b's, I need a way to spout off a's. And similarly, I must have at least 1 more a be generated. So here I'm going to have a variable called a, although it's kind of hard to distinguish now. Maybe I'll call it x, so that it's not hard to distinguish. So here I'm generating at least 1 more a, and then the x variable is going to spout off more a's if I need to. So a, x, or empty. And so therefore, if we have the number of a's and b's not being the same, one is less than the other, or the other way around. And so we're dealing with both of the cases independently and allowing ourselves to just deal in that specific case to generate the strings in that particular set. So hopefully that was interesting. Leave thoughts about these context-free grammars into the comments down below. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, thanks for watching, and I'll see you next time.